Here we have the graph of the line y equals 2x. That's a line that passes through the origin. The intercept is 0, as you can see. It's a line with a slope of 2 actually. Suppose that we want to take a segment of that line from x equals 0 to x equals 3 and rotate this segment about the x-axis. If we do that, we will generate a cone. To use integration to get the volume of this cone, we imagine that it is divided up into a number of thin circular discs. Well, we could think of this shape here as approximating a cylinder with a height of delta x, and the approximation to a cylinder will get better as delta x gets smaller and smaller. The volume of a cylinder is the area of the cross section, which is a circle, times the height delta x. So this point here is x. This is the leftmost point of this cylinder. Well, as I said, it's approximately a cylinder with height delta, a cylinder on its side. So what's this radius here, the distance of x to this? Well, that's just the value of the function at x, which is y, which is 2x. So here is the formula for the volume of a cylinder. It's just the area of the circular cross section times the height of the cylinder, where r is equal to 2x. So we have pi times 2x squared, and this is multiplied by delta x. Now, to get the volume of the cone, we have to sum all of these discs from x equals 0 to x equals 3, and then we have to let the height of the discs delta x tend towards 0. So we have to take the limit as delta x goes to 0. So the approximation becomes exact, because as you can see, this is not exactly a cylinder, but as delta x goes to 0, the approximation to a cylinder gets better and better. Now the pi is just a constant, so we can just pull that outside, and we saw in a previous video that we can rewrite this limit as the integral from 0 to 3 of 2x all squared, and we replace delta x with dx. We can take out the 2 squared, so we have 4 pi times the integral from 0 to 3 x squared dx. So we just perform this integral. So that's straightforward. The 4 pi is just a constant. So we have 1/3 x cubed from 0 to 3. We get 36 pi. Here's another example. This time we have the graph of y equals x squared, and we want to rotate the segment of that graph from 0 to 4 about the x-axis. So we'll generate a solid like this. So similar to before, we get the area of this cylinder, or this approximation to a cylinder, this shaded bit here. The radius is equal to the value of the function at x, which we know is x squared. So the radius is x squared, and the area of the circle then is pi times x squared squared. The area of a circle is pi r squared. So we let r equal x squared, we get pi r squared, and then we multiply by the height of the cylinder, delta x. So that's an approximation to the volume of this shaded region, and that approximation becomes exact as delta x goes to 0. So here's our sum. We're summing all these approximate cylinders from x equals 0 to x equals 4. And then if we take the limit as delta x goes to 0, we get the exact volume generated. So we just have to get the integral. So as before, delta x becomes dx, and the sigma notation is replaced with this integral sign, which is like an elongated s for the summation of this quantity. So this is a straightforward integral, and here's the answer. So in general, what are we doing? Well, here's the cone again. This was the equation of the curve. Well, it's a straight line in this case. For the cone it's 2x, but in general we're just taking the y value and squaring it. So in this case it's 2x, but here in general it's y, of course. So in general our integral will be pi times the integral of y squared dx. So this is our y here, it's 2x, so there it is. So we're squaring y, we're integrating with respect to x, and then our interval is from, well, it's from 0 to 3 in this case. In general it's from a to b. So here it is, we're just taking the limit of this sum. Now suppose we are rotating a curve about the y-axis. So here's our curve, y of x. We consider a sliver of that curve. It's approximately in the shape of a cylinder. The approximation gets better as its height, delta y in this case, approaches 0. So we just call this delta y now, because we're measuring along the y-axis for the height of this approximate cylinder. Here we have the radius of the cylinder, well, the radius of the lower circle. Again, as delta y goes to 0, the top circle will be approximately the same as the bottom circle, so we'll roughly have a cylinder. So what is this distance from here to here? Well, it's obviously just x. It's just the x value of this point. So to get the volume of a cylinder, we get the area of the circle, pi r squared. Well, the radius is x, so we've pi x squared, and we multiply by delta y. Now again, we want to take all such slivers, in this case say from 0 up to some value up here, or well, in general it's from y equals some value c. It doesn't have to be 0, but you know, the lower value is c and the upper value is d, and we're summing all such shaded slivers. That will give us an approximation to the volume of revolution, because we're summing cylinders exactly if we just take this sum. To make the approximation exact, we let the height of each sliver go to 0. We take the limit as delta y goes to 0. When we do that, we write dy for delta y, and this sigma symbol is replaced with an integral sign. We're integrating from c to d, say, in general. We don't see c and d on this diagram, but that's what we're doing in general. So you see this formula is similar to before if we just interchange x with y. Before we had the integral of pi y squared dx. Here we have the integral of pi x squared dy, because we're rotating about the y-axis. So let's take this example. We want to find the volume generated when the graph of y equals x squared between x equals 0 and x equals 1 is rotated around the y-axis. So here's the picture. So we want to rotate this segment here about the y-axis. So here's our formula. We are integrating with respect to y, and our limits this case are from 0 to whatever this value is. So remember, we're rotating this section around the y-axis, so we'll get some sort of a 3D shape, symmetrical about the y-axis. Okay, we need this value here, so this will be our upper limit. Well, that's just 1 squared, which is 1. So we're integrating from 0 to 1. Pi times x squared. Well, we can see that x squared is actually y here. So we need to have some function of y in here. So we just need to make x the subject of this. Straightforward here. So if we integrate y with respect to y, we get half y squared. And the upper limit gives us pi times a half, or pi over 2. The lower limit gives us 0. Let's do one more example. Suppose we want to rotate the line y equals 2 minus 2x around the y-axis for x between 0 and 2. We can see that when x is 0, y is 2. So the y-intercept of this line is at plus 2. The slope, the coefficient of x, is minus 2. So the y-intercept is somewhere up here. And the slope is minus 2. So since this is a point on the curve, if we increase x by 1, we decrease x by 2. Actually, it's more like we end up here. So when x is 1, y is 0. So we want to rotate this line about the y-axis for x between 0 and 2. So we want to rotate this part of the line about the y-axis. So the limits of our integration will be from this point to this point here. So when x is 2, what is y? Well, if we plug 2 in here, we get 2 minus 4, which is minus 2. So this is minus 2. So here's our formula. Our lower limit is minus 2, upper limit is plus 2. So we need to get x here. We need to make x the subject of this. So we add 2 to both sides and divide both sides by minus 2. Or sorry, we subtract 2 from both sides and divide both sides by minus 2. So here's x, and we need to square it. If we square this, we get a 4 in the denominator, so I'll take out that 4. And we have y minus 2 squared. We could use a substitution here. We could let u equal y minus 2, but I won't bother. I'll just square this out. So anyway, we have a straightforward integral. If we integrate this in here, we get a third y cubed minus 2y squared plus 4y. So plugging 2 in here, we get 8 over 3 minus 8 plus 8. Minus 2 cubed is minus 8. Here, same as before, minus 8. But now we have minus 8 here. We can take the pi over 4 out of this, and we have 8 thirds minus minus 8 thirds. Well, that's 8 thirds plus 8 thirds. That's 16 thirds. And we have minus this here, that's plus 16. 16 is 48 over 3. 16 plus 48 is 64. So we get 16 pi over 3. Now when we rotate this line about the y-axis, we get a cone, of course. And we know that the volume of a cone is 1/3 the volume of a cylinder that encloses the cone. 1/3 pi r squared h. So we can check our answer using this. So what's the radius? Well, it's this distance here, which is 2. R is 2. What's the height? It's the distance between 2 and minus 2. Well, that distance is 4. So we've 1/3 pi times 4 squared times 4. Sorry, this is 2 squared. So as you see, we end up getting 16 pi over 3.